Hello everyone. Today we are going to present our term project. The project is prepared according to the description of the system on chip design. That's why it consists of PL and PS design. In the project, the recorded WAV file, which is the audio file, will be loaded from the SD card and the process on the Zinc port, and later on the process according to the outputs and the sounds will be played on the result. Which numbers is placed will be displayed on the monitor by doing some sound processing. To understand the project with all principles, let's look at the flow chart. As you can see from the flow chart, it includes 6 different parts. Let's start one by one and demonstrate briefly. The first thing is to reach the already recorded WAV file, which are the inside of the SD card. And to do that, the PS part of the Zinc is used according to the x88ffh library and the SD card.h library. We can read if the SD card is formatted as FAT32. And later on, there are 3 different types of WAV files. There are PCM, and non-PCM and extensible format. To simplify, we used PCM coded WAV files which have 2 channels. After that, it will be decoded to read from the buffer. The important point here is to convert the hex to float in order to process the FFT part. In addition to that, we also added a Nyquist theorem to get over oversampling and overcorrelation. After all, the pure converted float data of the WAV file FFT are taken by the written FFT file inside of the PS, and only remain is to match the max FFT of the proceed data with the reference data by literature review. Those parts completed in PS parts, the results of the FFT also stored in the SD card. Later, maybe it can check by the MATLAB. It is time to explain the PL part simply.
Thank you for Abdullah for the nice presentation. In this part, we will more focus on in terms of the PL part. In the PL part, there were 2 significant items, which are the displaying monitor by the VGA and playing sound in the Zinc by using the driver of ADU 1861. Now we can continue with the Vivado open block design to check the PL parts, IPs one by one. There are different IPs, as you can see. The first important thing is the processor system reset. Reset is used to reset the processor and all its peripheral device in Vivado. To do that, fix its initial state. Later on, there is a XI interconnect, which is used to connect multiple XI buses and routing the data between the Zinc. There are also XI direct memory access is used to transfer data between the memory and the peripherals in Vivado. In addition to that, there is one more DMA for the VGA part, which is the video DMA. It is used to transfer video data between memory and the peripherals in the Vivado. If you look at the other parts, it can easily see that there is a video timing controller that is used to generate timing signals for the video output in the Vivado. Furthermore, there is also XC Smart Connect and the XC Force Streamed video out parts. Respectively, these are first one is to use for the bridge between the different bus protocols in Vivado. XI Force Streamed video out can be guessed from its name. It's generate the data to video output. The last part is the XC stream FIFO is used to buffer the XC stream data in the Vivado. Now we will look at all parts one by one in the details. The first important part is the clocking visor part. In this part, we use it because the processor system couldn't generate the actual frequency. We need the 180 megahertz. However, if we enter it in the processing system, it can decrease the actual frequency. Therefore, we add the clocking wizard at the beginning. to generate as the output for the 180 megahertz, both for the VG part and the sound part. Later on, there is a processor system reset. Processor system reset is used in Vivado to reset the processor and all of its associated peripherals to their initial states. Processor system reset, also known as PS reset, is used in Vivado to reset the, as I explained before, processor for Xilinx FPGA, and we can continue with the XI interconnect part. In this part, it stands for the advanced extensible interface. Interconnect is used in Vivado to connect and manage communication between the different components, such as the different components of the system on chip, to implement it on the Xilinx FPGA, for us Zinc 7000. The XE interconnect provides a flexible and efficient way, as it can see from its lines in the screen. Multiple XE compliant IP cores such as processor and the memory controllers, etc. As you can see, it's connected to smart connected, then it's going to our audio driver. There is a XE which is one of the most important part for the direct memory access part. In this part, it's a kind of a tool for designing FPGA-based system to transfer the data between the memory and the XE, advanced extendable interface bus, without involving the processor. As you can see, we didn't use the processor. However, we can use our memory and the XE part. The similar part, which is the video demo, is used for the VGA part. The same mission can be explained for it. Later on, there is a video timing controller. It is another important part. Also, it stands for, the acronyms is the VTC, is a module in the Vivado design to feed the design to control the timing signals for the video displays. Because in the video displays, as you can see, there is RGB data at the right corner. We need to select them by dividing them to the three parts as the 8-bit, 8-bit, 8-bit. Later on, the VTC can be used for different applications, such as the HDMI part, display port, VGA, etc. Another important thing, it's coming from the auto generation part in the Vivado, Access Smart Connect. At the upper corner, we can see left upper corner, yes. It is the feature in the Vivado that allows for easy connection between the, as you can see, coming from the XI, advanced XM interface buses, and it's automatically connects the approach X interface and generates the necessary information, interconnect logic, and it's saving time for the and reducing potential errors while designing the whole process. Another part is the XE4 stream to video out. This is a very simple part to convert the XE4 stream video data to format can be displayed on the monitor or the other video output device. The IP is support various video output. As you can see inside of it, there is a video format types, RGB, pixel per clock, native video output, etc. and the FIFO depth. Now, I want to explain the FIFO board a little bit later, then we can continue with our demo part. The XI stream FIFO. It is very commonly used to buffer and synchronize the data between the different clock domains. As you can see, we have two clocks at the beginning, and it is the different XE stream interface. It provides a FIFO buffer that can be used to store data and ensure that it's properly. It can be written even if the clock frequency of the day can be different, or if there is a difference in the data transfer rates. And this IP can be configured, support different data widths, dips, and the other parameters. At the right corner, you are seeing our RTL design, as I explained before, to divide our RGB data. That's all for the PL part. Now we will continue with our PS part a little bit. Later on, we will show our demo.
Hello, I'm going to continue with the PS part. Let me start to explain our main code. Those are the some libraries for the driver and the some image data for the display. some parameters that we define for the VGA for the display, such as the vertical and the horizontal pixel size and the other parameters. Those are the some data parameters that we call buffer, and those are the some functions for the audio DMIA driver, which is ADU 1761, to transmit the data to these ports to listen from this aux port, and those are some definitions for the for this component, and those are the functions that we defined upper part, some SPI parameter definitions to get to transmit the data, and those are the some initialize functions. Again, to transmit data, we use this, and in this part we are defining some playing wave file and doing some process. In here we are defining our files. We are reading files from the SD card. Then we are checking whether we got it or not. And then by using some memory, we are getting those data, and now we are ready to, if the data exists, we are ready to play and do some process like FFT and to write the results on the SD card. In this part, we are doing some encoding part, and in here we are doing we are converting hex to float format to calculate the fast Fourier transform. And in this part, we are using our FFT functions to calculate the FFT, to check whether the signal has which frequencies. And here we are doing some process of the FFT to check which peaks are exist in our FFT, and then we are detecting our numbers, which number is played on the which numbers are played on from the SD card, and then we are writing our specific FFT results to the SD card. In here we are ready to display on the VGA. We are doing some initializing, and then we are ready to display our data, and according to the results we are displaying our image accordingly. This is our main part, which we call the functions that we define in the upper part. And here we are saying you can press return to call the which file is located, and those are the some VGA functions that we defined to display the image. Let me first program the FPGA.
Thank you for Abdullah for the nice presentation. Now we will continue with our demo part. In the demo, as you can see, first we are programming our FPGA. Later on, launch to debug and the program. The PuTTY terminal program is open to control the SD card wave file, which file will be played. Now it's programming, as you can see at the right corner.
It is ready to run. As you can see, we can select the folders that were read from the SD card. For example, I am selecting the number 4 WAV file. I am pressing enter. It is calculating. It is taking FFT and writing the results.
As you can see on the screen, we are also showing the which number is played. We can try with another number to see the
For example,
sound.
let me try the 7. As you
As you
can
can
see.
see in the screen, we are seeing the 7. We can try one more time.
In the terminal, as you can see, the number is 7. It is 7. Let me try the source. It is calculated as you can see.
We are showing the
Also, the sound is played. I don't know whether you can hear or not. That's. Thank you for listening. We plugged in the SD card to our computer, and then we are checking whether the FFTs are recorded to the SD card or not.